All right, here we are for Honors Physics, Universal Gravitation, Worksheet 3, problem number 5. Problem number 5. Problem 5 asks, what would be the weight of a 67.5 kilogram person standing on Mars? And Mars has a radius of 3.39 times 10 to the 6 meters and a mass of 6.42 times 10 to the 23rd kilograms. So taking a quick look at this, I'm just going to jot some values down. Well, we're trying to find the weight, right? You say, what is weight? You say, well, weight, be careful, it's not mass. Weight is the gravitational force. It's how hard, in this case, Mars is pulling down on that astronaut. So let's go ahead and say, we're trying to find gravitational force. And clearly, we're not going to just use F as mg, little g, because little g, that's the acceleration due to gravity. It's a gravitational field strength. But it's different places in the universe. At the surface of the Earth, it's 9.8 meters per second squared, but not, or newtons per kilogram, but not on Mars. So we need to go ahead and pull out the big guns. Newton's law of universal gravitation. Fg is big G, m1, m2 over r squared. In this case, we're looking at an astronaut on Mars. So here's Mars, and here's our person. They're at the surface of Mars. How do you know it's an astronaut? I don't know. Let me put him in a helmet. There you go. Anyway, so you say, hey, we're trying to find the gravitational force between them. All right? Just as hard as the planet pulls down on the astronaut pulls up on the planet. We're showing the size of that with this equation. Okay, and this size, this force, that is the weight, right? Weight is that gravitational force from the planet. So all good, we don't have to rearrange the equation, that's nice. Big G, we know the value is 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. That is a set value in our universe, always the same. Now we have these. Now, one of them is the astronaut, and we say the mass of the astronaut, they told us was 67.5 kilograms, that's the mass. And so we know it's the mass because we recognize the units kilograms, that's how we know that's the mass. The other thing they tell us is the mass of the planet is 6.42 times 10 to the 23rd. 6.42 times 10 to the 23rd kilograms. That's the mass of Mars, which incidentally, that's about 1/10 the mass of the Earth. So anyway, just a side note. So if you ever think about those two planets, Mars is quite a bit smaller than the Earth. And then the radius of Mars, they tell us is 3.39 times 10 to the 6th meters. And incidentally, and don't forget that denominator needs to be squared. All right. Interestingly, the radius of the Earth is what? About 6 times 10 to the 6th. So really roughly half the radius. And you know the way volumes work, 4/3 pi r cubed for a sphere. So you're saying, hey, if I've got half the radius, that would be r cubed. It would be 1/8 the volume. So estimating this at being about 1/10 of it, you're like, yeah, I mean, it's compared to Earth, right? That's significantly smaller. And so we are expecting that gravitational field to not be as strong. But let's go ahead and do the calculation. So here we go. One thing I like to do, at this point, I'm just punching in the calculator, right? But I just want to point out, and just reminder for my students, that when I do calculations like this with all the exponents and powers of 10, I find it so much nicer punching in my calculator if I separate the powers of 10 out to the side and do those separately. So I might do this calculation in my calculator like this. I might do 6.67 times 67.5 times 6.42, because I can change the order I multiply in, it doesn't matter, right? And I'm going to do the powers of 10 off to the side. I'm going to divide this. Now, this is squared, so it's like 3.39 times 3.39 times 10 to the 6 times 10 to the 6. So I'm just going to do this part in my calculator. And the powers of 10, I can do by myself. Look, 10 to the minus 11 times 10 to the 23rd, that's 10 to the 12. 10 to the 6th squared, 10 to the 6th, that's 10 to the 12. 10 to the 12, 10 to the 12, they're just going to cancel out and be 1. So the powers of 10 all actually went away. That was really handy, this one. But the point is, I don't have to punch all those weird exponents in the calculator. And I feel like I'm a little less likely to make a mistake punching the calculator when I do it that way. So for a calculation like this, that's what I tend to do. You might give it a try yourself and see what you think. All right, try it a couple times. See if you think that's a little bit nicer. Let's see, 3.39 squared. When I do this calculation, I got something that was not right. Okay, so something is wrong here with my data. What did I do wrong? Oh, no. Mm-mm. Mm-mm. Mm. I don't know what I did wrong. That makes me think that some of my data going into this problem is wrong. Because what I got 251, and that's not right. Okay, that is not the acceleration to gravity on Mars. It's not heavier than Earth. You don't feel heavier. Oh, this is the weight. Oh, this is the weight. I'm calculating the weight, not the gravitational field strength. I'm so sorry. Yeah, so 251.5 newtons is what I got. Silly me. 251.5 newtons. Now, interestingly, you say, well, okay, that's nice, but that doesn't mean anything to me until I compare it with what the weight would be on Earth. So if I had a 67.5 kilogram person on Earth, right, 67.5 kilograms, I'm going to do the weight on Earth. That would just be, I can just use mg, right? And so my weight on Earth would be 67.5 kilograms times 9.8. So now I can actually compare it and see what it would be like. And this answer means something to me. 67.5 times 9.8. You get 661.5 newtons. That's what their weight would be on Earth. And so now you can say, oh, yeah, look, they are significantly lighter on Mars, right? You say that weight, the gravitational force is a lot lighter. In fact, if I do 251.5 over that, I can see it's 38% of the weight when you're on Mars. Okay, there you go. And you say, again, the fact that Mars is smaller volume-wise, like the distance being smaller, you're like, that would make the force bigger. But we also have a lot less mass pulling on you. It's a smaller planet. And so it ends up actually being less weight. So there you go.